So, you're very welcome to this Saturday session with Exam Revision on Leaving Cert Chemistry. We will begin this live session in just a moment. In this Saturday session today, what we are going to look at is we are going to explore first principles calculations for your titrations, which appear in question 1 of the Leaving Cert exam paper. We're also going to revise and mainly focus on the ethanoic acid titration. So we will revise the key theory that's associated with that, and we'll also complete then the calculations for this experiment, and we will go over 2016 question 1, which is an ethanoic acid exam question. So the first thing that we need to know is question 1 on the Leaving Cert exam paper will always be a titration question. There are a wide variety of titrations on the Leaving Cert Chemistry course, and they come from the chapters of water, acids and bases, which we will see some from today, and oxidation and reduction. Question 1 will always consist of a mix of theory and calculations. When we're talking about theory here, we're talking about theory specifically related to the experiment, but we're also talking about titration technique. So that could refer to the preparation of any piece of equipment, such as a burette, a pipette, or a volumetric flask. It will also maybe look for indicators, and you may also be asked for colour changes. Also, we are seeing in recent years that the last part of this question 1, they're pulling from the origin chapter, I suppose you could say. So for acid and bases, for example, with the ethanoic acid titration, they're pulling a question based on ethanoic acid from your organic families chapter. With oxidation and reduction, they're starting to bring in some reference to oxidation number, and for water then they're pulling theory from there as well. So it's just important to know that although the titrations are in question 1, you do need to have a little bit of a background on your theory of the titration that's in question and the chapter that it originates from. So for example, in this question today on our water crystallization experiment, we're going to see that you have to justify the choice of indicator that you use in your titration, and this will be coming from your pH and indicators chapter. A top tip that I have for question 1 is that you most certainly will need to know how to complete calculations by first principles. Up to a few years ago, you were able to use a formula to complete these problems. However, in recent years, the formula has not been able to be used, and you needed to approach the question through first principles. First principles will work for all titration calculations, even those that the formula can be used for. So it is a smart choice to pick first principles. You are cutting down on the amount of learning that you need to do, but also you are showing a better understanding of how the calculations in the Leaving Cert Chemistry course, and particularly in your titrations, actually work. So first principles is very important. The next thing I would say for question 1 is it is important to read the questions carefully, as answers will need to be specific and to the point. As with all questions in the Leaving Cert Chemistry paper, there is no real room for waffle when it comes to questions. You must get to the point, answer what has been asked, and be as specific as possible, because from looking at marking schemes you will be aware that certain words on the marking scheme are highlighted in bold, and without those keywords you don't get the marks for your question. So it's important to be specific and to the point. The next thing I would say to you is you should underline the keywords and action verbs of all your questions. So for example, you may be asked to state something, you may be asked to describe, you may be asked to identify. These are all different action verbs, and they all have a different way of answering them. So state and identify are quite similar. All you do is write down the answer, no need for an explanation. You literally just give the answer you're asked. A lot of those state and identifies will come with colour changes. However, if you're asked to describe means you need to explain, you need to give some steps, you need to give background, you need to show understanding. The describe questions will usually be worth somewhere between 12 and 15 marks. And what I always say is 1 point in a Leaving Cert chemistry paper is equal to 3 marks. So if your describe question is worth 12 to 15 marks, you should be writing somewhere between 4 and 5 points at least. Your state and identify might be worth 3 or 6. So depending on what's been asked there, you can figure for yourself how much you need to write, but it should be short and to the point. Now, as I said previously in this video, titration calculations should be completed by first principles, and you've only been able to use the first principles approach in recent years. Even if you are able to use the formula approach, which I will not discuss in this video, you will still be able to complete it by first principles. So first principles is the smart choice for your calculations, and I would say it is the only choice if you want to be getting a H1 in Leaving Cert Chemistry. If you don't learn first principles and you rely on the formula method and it doesn't work for you, or you're not able to complete it, you are automatically dumping your titration question and you won't be able to answer it. So the smart choice is to go with first principles. It is important to remember that for first principles may often only answer the first 2 or 3 parts of your calculation, and we're going to see that today in our water crystallization, because the water crystallization experiment has an extra part onto the end that we will need to be able to calculate. So that will involve some separate learning, but your first principles is always your starter point for your titration and will always be used for the first 2 or 3 calculation parts of an exam question. Now, as you can see down below, I've created a flow chart for you which goes through the steps of first principles, and these steps are very clearly laid out. As you can see above it, it tells you in the boxes, the coloured boxes, blue and red, it tells you what each step is used to find. And below in the white boxes is then it tells you how to complete each step. So for example, if you're asked to find the moles of your standard solution per titer volume, you would use the formula moles per litre, or the molarity, divided by 1,000. The reason you're dividing by 1,000 is because it's moles per litre, and there's 1,000 centimetres cubed in a litre, and you're multiplying by your titer volume. Now, one year it did ask this moles of your standard solution per centimetre cubed. So what you would do here is you would just divide by 1,000 and not multiply by anything. So it is important that when you learn these rules for first principles, that you can see that they are flexible and that you can interchange them, but that they are the basis of all of the answers to your questions, and that you will be able to answer questions using these set of steps, but you just have to read carefully in case there's any edits that you need to make to your formula and make them accordingly. And we'll see that in a few minutes when we complete the 2016 question. Step 2 of first principles then would always be to find the moles of your unknown solution in your titer volume. And to do that, you use the ratio, or the moles ratio, from your balanced equation, and you would compare your standard solution to your unknown, check the ratios. But the important thing with this step is to be careful of your volumes and that you use the correct volumes for your unknown solutions and your standard solutions. And we'll see this, as I've said, again in our 2016 question that we're going to go through in a few moments. The last thing then for first principles, and this is usually what the question will ask, it will ask you to find the molarity of your unknown solution. To find the molarity of the unknown solution, you need to complete the first 2 steps of first principles and then fill your answer in, moles by 1,000 divided by the titer volume, to get molarity. You're dividing by the titer volume and multiplying by 1,000 because you're looking for molarity, and molarity means moles per litre. Now, this should make sense to you from class and school. If it doesn't and you're still slightly confused, keep watching, because we're going to do a first principles calculation and I will take you through it step by step to help you understand. So let's go through the determination of the amount of water crystallization in hydrated sodium carbonate. So this is a titration in question 1. And as with all titrations, it's very handy to know what goes in your key parts of your titration so that it can help you with your theory parts of the experiment questions. So I always want to check what is present in my pipette, what is present in my burette, what indicator am I using, and what is the endpoint or the colour changes that I would be seeing. So, in the determination of water of crystallization in hydrated sodium carbonate, we know that we have hydrochloric acid in our burette. And this hydrochloric acid is of known concentration. So, we would say that what is in the burette is our standard solution. Now, it's also worth noting for this experiment that hydrochloric acid is a strong acid, and this will be helpful later on when you're coming to identifying your indicator. Another key thing that would need to be mentioned with your burette is another piece of equipment that we would use, which would be a funnel. A funnel would be used to fill your burette, and you would also need to make sure that below the tap of the burette is filled when you're filling it, etc. Now, if we move on to our pipette and our conical flask, we know that we have sodium carbonate present in our pipette and our conical flask, and I'm going to highlight that in blue for us. This is a solution of unknown concentration, so this is the concentration that we're going to probably be figuring out at some point in our calculations. When you're looking at your pipette and your conical flask, you should also be remembering that you use a pipette filler, and that is used to fill your pipette. And remember not to blow out the last drop in the pipette filler because it's calibrated for this. So next we have our indicator, and before we go any further, I will say to you that your indicator will go into your conical flask. The indicator that's used in this experiment is methyl orange, and the endpoint of the experiment, commonly referred to as the colour change, is from a yellow or orange, I'll write that in for you, yellow or orange to a pink or red colour. Now, before moving on, it's important that you know the balanced equation for this experiment. So for this titration, your balanced equation is as follows. So it's 2HCl plus Na2CO3, and that goes to give us NaCl, H2O, and CO2. And that should make sense to us because, again, it is an acid-base titration, giving us a salt and water. So let's dive into an exam question, and this is the 2020 question, question 1. So we're going to read through the question carefully. We're going to highlight our keywords. We're going to look for our action verbs, and we'll work from there. So washing soda is a cheap household chemical used for laundry, removing grease and softening water. Washing soda crystals are hydrated sodium carbonate, and the crystals lose water in dry air, becoming powdery in the process. So to determine the average value of X in the formula of Na2CO3 XH2O for a sample of washing soda, 3.6 grams of crystals, so I'm going to highlight that, 3.6 grams of crystals were dissolved in deionized water and made up to exactly 250 centimeters cubed. 25 centimeter cubed volumes of this solution were pipetted into a conical flask and titrated with a previously standardized solution of hydrochloric acid using a suitable indicator. And the balanced equation for the titration is as follows. So there we have our balanced equation there. So there's a little bit of information given to you at the start of the question. As you can see here, they give you a lot of information about your sodium carbonate. But we can also see that they give us some information about the hydrochloric acid, in particular that the hydrochloric acid has been previously standardised. And this is going to be important when we move further on into the question. Now, we've already highlighted our balanced equation in green, but I'm going to go over it now a little bit with you. So what I'm going to do is, we can see in the theory parts of the question above, I've highlighted the hydrochloric acid in yellow, so that's what I'm going to do here. And I've highlighted anything got to do with the sodium carbonate in blue, and that's what I'm going to do. The next thing to look at would be to look at your ratio. And we can clearly see that this is a 2:1 ratio. So we have twice as much hydrochloric acid as we have sodium carbonate when it comes to the number of moles that are present. And this is going to be very important when we come to our first principles calculation, which we will meet later on in this question. So let's move into the actual parts of the question and what are they asking. So if we look at part A, we can see our first action verb here is to identify. And the question asks you to identify a primary standard that could have been used to standardize the hydrochloric acid for this analysis. So they're basically asking you, what primary standard could you use to figure out the concentration of the hydrochloric acid before undertaking this experiment? Now, this question is worth 5 marks and it is an identify, so you just need to write down what the primary standard is, and that's it. There's no need for any explanation here. Part B then of this question. Part B, the action verb here is to describe. So you're going to have to give some explanation. It asks you to describe how the 250 centimetre cubed solution of washing soda was prepared, starting with 3.46 grams of washing soda measured out accurately on a weighing boat. Now, we can see here from this question that it is worth 12 marks, and I always say 3 marks on a Leaving Cert chemistry paper is equal to 1 point of information. So the fact that there is 12 marks here, you will need, that is 3 by 4, so you will need 4 points of information working out at 3 marks each. And we'll see on the next part of this video when I go through the answers that I always tend to give an extra point of information just in case the marking scheme changes and your answer maybe isn't hitting the mark. But because it's describe, you need to give a description and provide some detailed information. And with these questions in particular, they are going to be looking for equipment that you've used and the titration technique if it's necessary. Part C then. Part 1 is asking you to name a suitable indicator for this titration. So again, that's fairly straightforward. You just name the indicator. C part 2 asks you to justify your answer. So justifying your answer here basically means give a reason why you chose the indicator you did in part 1. And then part 3 says, using the indicator, what colour change was observed in the conical flask. Now, once you see the word colour change, you must give 2 colours. So I always say with a colour change, you should give the before colour and the after colour. And that will guarantee you your marks in a question like that all of the time. Part D then. Part D is the really important part of this question. It's worth 21 marks, so it's worth just over 40% of the question. And what we're looking at here is our calculation. So it says, on average, 21.5 centimetres cubed of 0.12 molar hydrochloric acid were required to completely neutralise the 25 centimetres cubed of the washing soda. Now I'm going to stop there because, as you can see, as I was reading that out, I highlighted those figures in different colours. So as I have done with the top part of the question and the balanced equation, I highlighted anything got to do with the hydrochloric acid in yellow and anything got to do with the sodium carbonate or the washing soda in blue. So what you're asked to do in this question is you're asked to find by calculation some of the following. So you're asked to find the average number of moles of hydrochloric acid used in this titration. So what they are asking you there is they are asking you for the number of moles per your titra volume, and that's what we will learn for first principles. The second part is asking you to find the number of moles of Na2CO3, which is sodium carbonate, neutralized in each titration. Now, you can find this by using your balanced equation and looking at your ratio, because you will have previously figured out the number of moles of HCl used in the titration, so you can go back to your balanced equation to figure out the number of moles of sodium carbonate used. That will be for your titration. So for part 3 then, it asks you to find the number of moles of Na2CO3 in 250 centimetres cubed. So there, you will use your answer from part 2 and you will multiply it such that you get 250 centimetres cubed. And we'll go through this on the next slide. Part 4 is asking you to find the mass of sodium carbonate in 250 centimeters cubed. And whenever I see mass, I'm automatically thinking I have moles, I'm looking to get mass, so I'm going to have to do something with my molecular mass or my MR. Part 5 then, they're asking you to find the mass of water and hence the number of moles of water in 3.46 grams of crystals. Now, with this question, you need to be careful. They're trying to catch you out here. There's two parts hidden within part 5. So the first one, you're asked to find the mass of the water of crystallization and hence the number of moles of water. So when we're doing out this calculation on the next few slides, we will be doing those two parts in part 5, but you need to spot that they're looking for two calculations within one there, and that's very important. A lot of students will skip over that and lose marks. And then part 6 is asking you to find the ratio of moles of water of crystallization to moles of sodium carbonate. So when I see the word ratio, I automatically think either your balanced equation or I would think division. And because we're using the balanced equation further up in part 2, I'm going to think, right, ratio means divide, so I'm going to be dividing something. But also you can see in part 6, they say hence find the value of x. So they are going to want you to find out what is the value for x up here that I'm highlighting at the top part of the question, or that I'm going over now. So as you can see, part 6 also has two calculations hidden within one part. Another very important part in this question, and I'll underline it rather than typing it or highlighting it, is they ask you for your answer correct to the nearest whole number. And that's important because there will be a mark lost in the case of not rounding to the nearest whole number. So it is important that you follow that. So now that we've gone through the question, broken it down, highlighted our action verbs, highlighted keywords, given a few pointers on what we're going to do, let's go and answer this question now together. So to answer this question, we're going to start with the theory parts of the question, and that is parts A to C. So part A asks us to identify a primary standard that could be used to standardize the hydrochloric acid solution for this analysis. So here they're asking you, what primary standard could we use to figure out the concentration of the hydrochloric acid that we're using in this titration? And the answer is very simple because it's an identify, so you just need to state your answer. And your answer for part A is anhydrous sodium carbonate. That is the primary standard that you will use to standardize your hydrochloric acid solution prior to completing this experiment. Part B then, it asks you to describe how 250 centimeters cubed of your washing soda was prepared, starting with 3.46 grams of it measured out accurately in a weighing boat. Now, as I mentioned in the previous slide, this is worth 12 marks, we know that 3 marks is equal to 1 point of information. So if we have 12 marks, we must have 4 points of information. And I usually give a fifth one. The main reason I would give a fifth one is you never know what way the marking scheme is going to work out. You never know what steps that they're going to be looking for in particular. So I put them all in and I ensure that I maximize my full marks because I want to get a H1 out of this question. Now, before we start giving the actual answer to this question, it's important that we can read from the question what has already been stated, that we're not restating what's in the question. So we can see here that they're asking us to describe how the solution was prepared, starting with 3.46 grams of washing soda that was measured out accurately on a weighing boat. So you will get no marks for saying that you weigh out the 3.46 grams of the washing soda because they've already told you in the question that that has been accurately done using a weighing boat. So that is not one of the points that's allowed in this question, and that needs to be noted straight away from reading it carefully. So let's take a look at these steps together. So the first step would be to take the 3.46 grams of washing soda and to dissolve it in some deionized water in a beaker that has been previously rinsed with deionized water. And then I would stir using a stirring rod to help dissolve this. The next step then would be to use a funnel to transfer this solution that's in your beaker into a 250 centimeter cubed volumetric flask that has been previously rinsed with deionized water. So here I'm showing you that you need to mention you've used a funnel to transfer the solution into the volumetric flask and that the volumetric flask has been previously rinsed with deionized water. It's important that you know you only rinse your volumetric flask with deionized water. You do not rinse it with the solution it is to contain, because we are adding a specific volume of this solution to our volumetric flask and diluting it then using deionized water. So rinsing with deionized water is the only pre-step process that you need to take in this titration. Step 3 then says you add the rinsings of the beaker into the volumetric flask, and that is very important. You need to pour some deionized water into your beaker, swirl your beaker, and then add this rinsing into your volumetric flask. This ensures that you are maximizing your yield and ensuring that no residue from your washing soda is left behind in the original beaker. Step 4 then says that we add deionized water until the bottom of the meniscus is in line with the graduation mark, and that is extremely important. And I would also put in here that the water should be added dropwise towards the end, because that will help ensure that there is good accuracy in your meniscus. The final step then is to invert the volumetric flask 20 times to create a homogeneous solution. So as I've said there, I've given 5 points of information. They're very detailed. I've mentioned all equipment that I've used in each step, so I'm guaranteeing myself full marks there for that part of the question. So if we look at part C now, we can see that C part 1 is asking you to name a suitable indicator for this titration. Part 2 is asking you to justify your choice of indicator, so you must give a reason. And part 3 then asks you, using this indicator, what colour change is observed. So remember, when you're being asked for a colour change, you need to give what it is before the titration starts and what it is when the titration is complete. So, C part 1, name the indicator used in this experiment. The indicator used is methyl orange. Now, part 2 asks you to justify your answer, so you must give a reason. And the reason here is that hydrochloric acid is a strong acid and sodium carbonate is a weak base. And with a strong acid and a weak base, we should know from our pH and indicators chapter that with a strong acid and a weak base, we use the indicator methyl orange, as that is the best indicator to work within the pH range of this titration. Then it asks us to, using the indicator, what colour change was observed in the conical flask at the end. So the colour change that we observe at the end point of this experiment is an orange to pink colour. And you can clearly see there that I have given 2 colours, what it is before and what it is after, because I'm maximising my marks in this question. Now, let's move on to part D, and part D of this question is all of the calculations. And as I said earlier on in this video, this is quite a substantial part of the question. It's worth 21 marks out of 50, which is 42% of this question. So it says, on average, 21.5 centimetres cubed of 0.1 molar hydrochloric acid were required to completely neutralise 25 centimetres cubed of the washing soda solution. So as you can see there, I've highlighted, as I did in the earlier part of the question, my acid pieces of information in yellow and my base pieces of information in blue. Now I am going to write down the balanced equation for us that we have it. It's 2HCl plus Na2CO3 goes to 2NaCl plus H2O plus CO2. So this will help us later on with our calculations. So if we're looking for part 1 here, part 1 asks us to find the average number of moles of HCl used in this titration. So the average number of moles of HCl, so that's yellow there. When they're asking for the average number of moles of HCl, what they're simply asking you for is the moles per your titer volume, and that is step 1 of first principles. So this is the moles of your standard solution. We know this is the standard solution because a standard solution is a solution of known concentration, and we know that the concentration of our HCl is 0.12. So I know that I have moles per litre, or molarity, that is 0.12, that I divide that by 1000, and the reason you're doing that is molarity is moles per litre, so dividing that by 1000 gets rid of the litre, and we multiply by the titer volume, and the titer volume here is 21.5. And when we put that into the calculator, what we get is we get 0.00258, and that is moles per 21.5 centimeters cubed. And that is the answer to part 1. So next we move on to part 2, and we can see here part 2 is asking us for the number of moles of Na2CO3, which is our base, neutralized in each titration. Now, because I have the number of moles of my hydrochloric acid, I can use my balanced equation in this part to figure out the number of moles of my sodium carbonate. So this is actually step 2 of first principles. So I'm going to answer this in blue because it's linked with my base, and we're looking for the moles of our sodium carbonate in each titration, neutralized in each titration. So that's looking for your moles of your unknown solution in your titer volume, and we can use our balanced equation. So my balanced equation is 2HCl is to Na2CO3. So I can clearly see from my balanced equation that is a 2:1 ratio. So I have, from my previous part, I have 0.00258 moles per 21.5 centimeters cubed of my HCl. So because it's 2:1, it must mean I have twice the amount of moles of HCl as I do Na2CO3. So that means I will be dividing this concentration by 2. So I will get 0.00129 moles of my sodium carbonate, but this is per the titer volume of the sodium carbonate, and we know from up here that that is 25 centimeters cubed. So that is 0.00129 moles per 25 centimeters cubed, and it's very important that you check your volumes when you are doing first principles and that you're matching them up correctly with your acids and your bases. So that is the answer to part 2. So if we take a look at part 3 then, part 3 is asking you for the number of moles of your Na2CO3 in 250 centimeters cubed. Now, this is basically the third step of first principles, because the third step of first principles asks you to find the molarity of your unknown solution. But molarity would mean moles per litre, but here they're only asking you for moles in 250 centimeters cubed. So rather than going to your last step of your first principles, there is a very easy quick step that we can do, because we know from the previous part that we have 0.00129 moles of our sodium carbonate per 25 centimeters cubed. So if I want to go from 25 centimeters cubed to 250 centimeters cubed, I can simply multiply by 10. So that must mean that I must multiply the number of moles by 10 also. So that means we get 0.0129 moles per 250 centimeters cubed, and that is enough to answer part 3. So moving along then to part 4. Part 4 is asking you to find the mass of sodium carbonate in 250 centimeters cubed. So what they are simply asking you here is they're asking you to convert the answer that you got in part 3 into grams. And we know that if we want to go from moles to grams, that we must multiply by the molecular mass. Now, this is the mass of sodium carbonate, so we are going to be getting the MR of your Na2CO3. So let's figure that out. We know it's 23 plus 23 plus 12 plus 16 plus 16 plus 16. And that gives you 106 grams. So that is the molecular mass of your sodium carbonate. And this is anhydrous sodium carbonate. So what we do is we get our 0.0129, we multiply that by 106, and that gives us 1.3674 grams per 250 centimeters cubed, and that is the answer to part 4. Right, so let's move along to part 5. Let's take a look. Part 5 asks for the mass of water of crystallization and hence the number of moles of water in 3.46 grams of your crystals. So the first part here is they're asking for mass, and the second part is that they're asking for moles. So let's do this. So for part 5, the first part they're looking for the mass of water of crystallization. Now, from the earlier part of the question, I've just popped it in here, we know that we have 3.46 grams of Na2CO3X H2O. So let's write that down. We have 3.46 grams of Na2CO3X H2O. So that means we have 3.46 grams of the hydrated part. Now, from part 4, we were working with anhydrous sodium carbonate. So we could say that we have 1.3674 grams of just Na2CO3, because that's what we figured out in part 4. So this means that there is no water present in this 1.3674 grams. So if we wanted to figure out how much water there is present, we can just simply subtract those. And when you do that, you would get 2.0926 grams of water in 250 centimeters cubed of solution. And there we have calculated the mass of water of crystallization present in 3.46 grams of your crystals. So the second part of this part 5 asked us then to find the number of moles of water in the 3.64 grams. So I currently have the number of grams of water that is present. So if I want to convert that to moles, what I need to do is, we know to go from grams to moles that we need to divide by the molecular mass. So this section here is on moles, I'll just mark that. So we need to know how many moles of water there is in 2.0926 grams of it. So the first thing you'll do is you'll get your molecular mass of water, H2O, and we know that that's 1 plus 1 plus 16, which is 18. So I can now take the 2.0926 grams of H2O, divide that by the molecular mass of H2O, which is 18, and that will give me that there is 0.1163 moles of H2O in 250 centimeters cubed of our solution, and that is part 5 completed. So part 6 then asks us, what is the ratio of moles of water of crystallization to moles of sodium carbonate in the crystals, and then they hence ask you to find the value of X. So what we're looking at here is we want to get ratio. So ratio would be water of crystallization. So let's write that down. So we can see that the number of moles of water of crystallization that we have in 250 centimeters cubed is 0.1163. And we're comparing this to the number of moles of sodium carbonate, anhydrous with no H2O in it, in 250 centimeters cubed, and that was figured out here in part 3, which is 0.0129 moles. Now, they then ask you to hence find the value of X, correct to the nearest whole number, where X is the number of water molecules that's present. So using this ratio, we can actually divide them, because ratio means divide. So I can take my 0.1163, which is the number of moles of water of crystallization, in 250 centimeters cubed, and divide that by 0.0129, which is the number of moles of anhydrous sodium carbonate present in 250 centimeters cubed. And if I do that, I will get that my x value will be equal to 9 when I round it to the nearest whole number. So the actual chemical formula in this question for my hydrated sodium carbonate is Na2CO3 by 9H2O. And at that point, this calculation for the 2020 question 1 of your water of crystallization titration is now complete. So just before we finish up, I just want to show you what the Leaving Cert Chemistry Exam Revision website looks like. So as you can see here, I have all the units of the Leaving Cert Chemistry course done out for you, units 1 to 11, and there's also a folder there on exam preparation. So for example, if we click into the oxidation and reduction section of unit 6, we can see that I have 5 videos here on all of your oxidation reduction titrations. Those videos go through the experiment, the method, common exam questions, and any calculations. And there's also a Leaving Cert Chemistry sample solution done out for you for an exam question of that experiment. You can also see that there is a self-correcting quiz, a PowerPoint presentation, and of course the H1 standard notes. There is also an area where you can build your own exam to test yourself on the titration questions or any part of the Leaving Cert Chemistry course, and marking schemes are also provided. So the standard plans on ExamRevision.ie are $19.99 a month, and premium plans are $29.99 a month. And for today, on this Saturday session, if you wish to sign up to a standard or premium plan for Leaving Cert Chemistry with Exam Revision, you can use the discount code LCChem20, and that will get you 20% off. So if you need any guidance for Leaving Cert Chemistry, don't forget you can get in touch with us here at Exam Revision. We're on Twitter, Instagram, TikTok, Facebook and YouTube. And of course, you can visit our online learning platform, ExamRevision.ie, where you will get access to the full Leaving Certificate Chemistry course done out in video format, H1 standard notes, PowerPoint presentations, and of course self-correcting quizzes and access to previous exam papers. So that's it for today's Saturday session. Thanks for joining in, and hopefully we'll see you at the next Saturday session very soon.